Usually when we talk about a medical diagnosis, there's this um, underlying expectation of absolute precision.
Right, like you want a clear answer.
Yeah, exactly. You break your arm, the x-ray shows that jagged white line on the film, and the doctor just points and says, there it is.
It's visible.
It's categorized, yeah. And honestly, it's comforting.
Well, it gives us a sense of control, right? When we can see the mechanism of the problem clearly, we just assume we can engineer a clean solution.
But then you step into the world of predicting the Earth's climate, and suddenly that x-ray machine is completely inadequate.
Oh, completely.
We are trying to diagnose the future of our own planet, and the landscape is incredibly murky. Like, the Earth system doesn't pose for a clean diagnostic image.
No, far from it. I mean, the Earth is a chaotic, non-linear system of fluids. Air and water constantly interacting over a jagged, rotating sphere.
Right. And that reality brings us to our mission for today's deep dive with you, because we are exploring a truly fascinating cutting-edge paper titled A Framework for Hybrid Physics AI Coupled Ocean Models.
It's a great piece of work.
It really is. It's authored by El Zana and this really extensive team of researchers from places like NYU, Princeton, Columbia, and NOAA. And our goal today is to understand how these scientists are fundamentally rewiring our climate simulations.
And doing it in a very novel way.
Exactly. The wild part is they aren't doing it by throwing out the old physics rule books. They are teaching artificial intelligence to fill in the microscopic invisible gaps that our absolute biggest supercomputers simply cannot catch.
Which really represents a profound shift in the philosophy of the science itself.
Yeah.
Yeah, because we are moving away from pure classical mathematical theory into a hybrid space. It's this marriage of classical fluid dynamics and modern machine learning.
Wow.
And what I find so compelling about this paper is that it isn't just, a theoretical exercise sitting on a whiteboard. They are making operational structural changes to state-of-the-art models that are running right now.
So if you've ever wondered why the weather forecast sometimes just completely misses a major storm.
Or why long-term climate predictions constantly need to be updated.
Right. Or, frankly, how artificial intelligence is actually being used in the real world beyond, chatbots and image generators. This is the exact intersection you need to look at.
Absolutely.
Because climate models dictate our future. They determine where cities will build seawalls, how farmers will plan their crops decades out, and how global policies are shaped. But they have these built-in blind spots.
Massive blind spots.
And to help us decode the complex meteorology and the machine learning jargon behind fixing those blind spots, I've got the perfect guide sitting right across from me. We're going to unpack this piece by piece.
Well, I'm very much looking forward to it. There is a vast amount of intricate science here.
Yeah.
But the core mechanisms, the how and the why, are actually incredibly intuitive once you strip away the dense equations.
Okay, let's unpack this right from the start. To understand how AI is fixing these models, we first have to understand why the models are broken in the first place. We have to begin with what the researchers call the fundamental limitation of numerical modeling. So let's talk about the pixel problem of planet Earth.
I like that framing.
Thanks. When scientists say they are modeling the climate, what is the actual physical process happening inside the computer?
Well, the easiest way to visualize it is to imagine wrapping the entire Earth in a giant, invisible, three-dimensional wireframe mesh.
Okay.
We divide the atmosphere and the ocean into millions of individual 3D boxes or grid cells.
Like a Minecraft world, basically.
Exactly like that. And inside every single one of those boxes, the computer uses the fundamental laws of physics, specifically fluid dynamics and thermodynamics, to calculate a set of variables.
Okay, so it's looking at the air and water.
Right. It calculates the temperature, the wind speed, the humidity, the salinity of the ocean, the water currents.
Got it.
And once it has those numbers for every box, it steps forward in time, maybe by a few minutes, and calculates how the air and water in one box push against and exchange heat with the boxes immediately next to it.
So it's essentially a massive planetary scale spreadsheet, constantly updating itself based on the laws of physics. More boxes, smaller boxes, better prediction.
In theory, yes. But we collide instantly with a massive wall, which is finite computing power.
Ah, right.
Even if you network together the world's most powerful supercomputers, there is a strict, hard physical limit to how small we can make those grid boxes.
So how big are they right now?
Currently, the spatial resolution of a standard operational global ocean model might have grid boxes that are roughly 10 to 100 kilometers across.
Wait, let me stop you there. A standard model uses boxes that are 100 kilometers wide.
Yes.
So anything smaller than 100 kilometers just isn't simulated.
It exists in reality, of course, but it is entirely invisible to the mathematics of the model. The model simply cannot see it.
Wow.
We call these invisible phenomena subgrid scale processes. They are, by definition, smaller than the grid spacing.
And I imagine a lot happens in 100 kilometers.
An incredible amount. In the ocean, this encompasses a massive amount of crucial physics. It includes vertical processes like deep convection, the turbulent boundary layers where the ocean surface constantly interacts with the atmosphere.
Where the waves are crashing and mixing.
Exactly, and the complex microphysics of how clouds form and dissipate. It also includes horizontal processes, primarily things called mesoscale and submesoscale eddies.
Let's define that. Eddies are basically whirlpools, right? Swirling currents.
Correct. They are swirling, turbulent vortices of water. And in the ocean, these eddies typically range from 10 to 100 kilometers in diameter.
Oh, man. So they exist right in that blind spot.
Precisely. Because they are smaller than the grid, the model cannot explicitly simulate their rotation or their movement.
It's like trying to recreate a high-definition photograph of a human face using a handful of chunky Legos.
That's a good way to put it.
You get the rough shape, you know roughly where the forehead is, where the jawline is, but you completely miss the wrinkles, the pores, the eyelashes.
That is an excellent visualization. But we have to take that analogy a step further to understand the crisis in climate modeling.
Okay, how so?
Because in a photograph, an eyelash is just a cosmetic detail. If you miss it, you still essentially have a face.
Right.
But in the fluid dynamics of the climate system, those eyelashes, those microscopic turbulences and subgrid eddies, are not just cosmetic. They are active mechanical gears driving the whole machine.
Because they don't just sit there. They interact with the larger ocean.
Exactly, they cascade.
Yeah.
A single 50-kilometer ocean eddy might seem completely insignificant compared to the vastness of the Pacific Ocean.
Sure.
But there are millions of these eddies constantly spinning, and together they act as massive global conveyor belts. They transport staggering amounts of heat, salt, and momentum across the planet.
Wow.
They mix the warm water from the equator down into the deep, cold layers.
I see. So if you get the microscopic turbulence wrong or you just ignore it because your Lego blocks are too big to build it, your macro climate forecast isn't just a little blurry, it actively drifts off course.
It drifts catastrophically. If your model ignores how those small eddies stir the ocean, your prediction for massive currents like the Gulf Stream will eventually warp.
That makes sense.
And if the Gulf Stream is simulated in the wrong place, your prediction for the temperature and agricultural viability of Northern Europe 50 years from now will be fundamentally wrong.
Which begs an enormous question. If we know our computers aren't powerful enough to make the grid smaller, and we know we're missing these crucial heat-transporting whirlpools, how have scientists been making climate projections for the last 40 years? What's the Band-Aid?
Right. Well, the historical solution is a concept called parameterization.
Parameterization.
Yes. This is how physicists have traditionally tried to solve what they call the closure problem. The logic goes like this. If we cannot afford the computing power to simulate the turbulent eddy directly, we will write a mathematical approximation.
Okay, so a shortcut.
Exactly. We create a formula that guesses the average effect of all those missing eddies on our large 100-kilometer grid box.
So the model basically says, I can't see the tiny whirl tools, but based on the overall temperature of this giant box of water, I'm just going to assume they are mixing things up by exactly this much. It's an educated guess.
It is an educated, physically based guess, but traditional parameterizations have some profound flaws. The most glaring is their reliance on something called scale separation.
Scale separation, meaning you assume the big stuff and the small stuff are completely different animals.
Exactly. Traditional formulas assume that the microscopic unresolved turbulence operates on a completely different physical scale than the large resolved ocean currents, and that the two don't get messy and overlap.
Okay, but I'm guessing they do.
They do. And as supercomputers get slightly better and we shrink our grid down from 100 kilometers to, say, 25 kilometers, that clean separation completely breaks down. We enter a gray zone.
Right.
The old mathematical approximations are rarely scale-aware.
meaning a formula meticulously designed to guess the turbulence in a 100-kilometer box might completely lose its mind and output garbage if you suddenly apply it to a 25-kilometer box.
Yes, exactly.
Because at 25 kilometers, the model is starting to partially see the edges of the eddy.
Precisely. It starts double counting the physics or getting the math entirely backward. Furthermore, these traditional approximations require constant, painstaking tuning. They rely on ad hoc parameters.
Ad hoc parameters, so fudge factors, little dials and knobs in the code.
Yes, fudge factors. Dials that scientists have to manually adjust based on sparse observational data from the real world.
Like dropping buoys in the water.
Right. They look at measurements from scattered ocean buoys or passing commercial ships, and they tweak the formula to try and match reality. But the ocean is massive, and human observation is incredibly sparse and noisy.
I can imagine.
We are practically blind in vast regions of the Southern Ocean, for example.
It sounds like trying to tune a massive million-piece orchestra while blindfolded and half the instruments are in another room.
That's a very accurate way to put it.
And here's the really bleak part.
Meh.
We can't just wait around for a supercomputer big enough to solve this. Because Moore's law, the rule of thumb that computer processing power doubles every 2 years, is fundamentally slowing down as we hit the quantum limits of silicon.
Yes, we are hitting a physical wall.
We can't just wait for a computer big enough to shrink the global climate grid down to a millimeter.
That would literally take centuries of continuous computing time with current architectural paradigms. And the researchers behind this paper understood that intimately.
So they needed a new plan.
They recognized that the field required a completely different paradigm. If we can't guess the missing physics with rigid formulas, and we can't wait for a magical supercomputer, they asked a radical question. What if we just teach the model what it's missing?
And that realization is where we cross the bridge from classical physics into the realm of artificial intelligence. They decided to use machine learning to learn the subgrid physics. But my immediate thought is, how? An AI needs training data. ChatGPT read the whole internet. But you just said human observations of the ocean are terrible. You can't train a neural network on a handful of buoys floating in the Atlantic. Where's the data coming from?
That is the genius of their methodology. They generate their own perfect ground truth.
Oh, really?
Since the real ocean is too vast and poorly observed, they use what are called high-fidelity simulations.
But wait, if they have high-fidelity simulations that perfectly model the ocean, why do we have a chunky Lego problem in the first place? Why not just use those?
Because these high-fidelity simulations are computationally excruciating. We are talking about running a large eddy simulation, or LES.
Like an LES.
An LES does exactly what it sounds like. It makes the grid boxes so microscopic, sometimes down to mere meters or centimeters, that it explicitly simulates every single tiny swirl and turbulent vortex.
Oh, wow.
It tracks the exact physics of the turbulence without guessing.
So why not run an LES for the whole Earth?
Because to run an LES for a tiny patch of ocean, say, a patch just a few hundred meters across for a simulated time of just a few days, might take a supercomputer a massive amount of time and energy.
Just for a few days?
Just a few days. To run an LES globally for a century-long climate forecast, well, the compute time required would outlast human civilization.
Ah, I see. It's a microscope. You can look at a tiny drop of water perfectly, but you can't use a microscope to look at the entire Pacific Ocean at once.
Exactly. And the researchers also use something called second moment closure, or SMC.
Okay, you're going to have to translate that for me. What is a second moment closure?
Let's break it down into statistics. If you look at a river flowing, the first moment in statistics is the mean. It's the average speed and direction the whole river is moving.
Simple enough.
The second moment is the variance. It's the turbulence. It's how much the water is violently fluctuating away from that average speed, spinning off into little eddies.
Okay, got it.
Second moment closure is a highly complex mathematical framework that explicitly tracks and calculates that violent variance rather than just tracking the average flow. It is incredibly accurate, but again, far too computationally heavy to run inside a 100-year global climate model.
So they use these ultra-expensive microscopes, the LES and the SMC, to simulate tiny patches of the ocean under very specific conditions.
Yes. They simulate a tiny patch of ocean under a hurricane, then a patch under a calm, sunny sky, then a patch during a winter freeze.
Building a library.
By doing this thousands of times, they generate a massive, noise-free, mathematically perfect data set of exactly how water mixes and transfers heat at the microscopic level under almost any weather condition imaginable.
Okay, so they've built a pristine library of microscopic ocean physics. But the global climate model is still operating with chunky 100-kilometer Lego blocks. How does the AI connect the perfect microscope data to the chunky global model?
Through a fascinating mathematical procedure called coarse graining.
Coarse grain.
Yes, this is the core mechanism of how the AI learns. The scientists take that perfect ultra-high resolution data and they intentionally blur it.
They blur it.
They apply a spatial filter that essentially downgrades the resolution until it perfectly matches the chunky 100-kilometer grid of the global model.
It's like taking a pristine 4K video
Yeah.
and applying a massive pixelation filter until it looks like an old VHS tape.
Yes, and because they possess both the original 4K video and the blurred VHS tape, they can perform a deeply revealing calculation.
What's that?
They can subtract one from the other. They can calculate exactly what physical forces, how much heat transport, how much momentum were lost when the image was blurred. They compute the exact subgrid forcing.
Subgrid forcing.
Right. It's the precise mathematical gap between the perfect reality and the chunky approximation.
Oh, that's brilliant. They are creating an answer key. They know
Yeah.
exactly what the chunky model is missing.
Exactly.
Yeah.
And once you have an answer key, you can train a machine learning algorithm. They show the AI the blurry, low-resolution variables, the large-scale temperature, the slow average currents, and they ask it to predict the exact missing high-resolution subgrid forcing.
And through millions of iterations, the AI learns the invisible mapping between the large-scale weather patterns and the microscopic turbulence.
It does. So instead of a human physicist spending a decade trying to write a single, rigid mathematical formula with a bunch of manual dials to guess the turbulence, the AI just looks at the data and naturally intuits the incredibly complex nonlinear relationships.
It learns the physics from the data.
It fundamentally bypasses the need for human-authored ad hoc approximations.
Wow.
But that immediately leads to the next massive engineering hurdle, because AI is not just one uniform thing. You can't just plug the architecture behind a text generator into a fluid dynamics simulator.
Right.
Choosing the right brain for the model is a delicate, highly consequential balancing act.
Right. Because if I'm a scientist building this, what kind of neural network am I actually writing into the code? Because if it's too simple, it won't understand the physics. But if it's too complex, won't it just freeze the supercomputer anyway?
You've hit on the exact trade-off: structural error versus computational complexity. To solve this, the researchers systematically tested 3 very different tiers of machine learning models.
Let's walk through these brains. What is the first tier they looked at?
Tier 1 is the heavyweight champion of deep learning: convolutional neural networks, or CNNs.
CNNs.
Yes. These are massive, highly complex, deep learning models. If you've ever seen an AI that can identify a cat in a photo or power a facial recognition system, it is likely using a CNN architecture.
Okay, but the ocean isn't a face or a cat. Why use an image processor to calculate water temperature?
Because CNNs are uniquely phenomenal at capturing what we call non-local dynamics. A CNN doesn't just look at one single pixel in isolation. It uses a stencil, say, a 21 by 21 square grid of pixels, and it sweeps that stencil across the data. It learns to find patterns not just in one spot, but in how that spot relates to the water 200 kilometers away.
Ah, so it can see the larger structures. It can see how a big storm system is interacting with the ocean over a huge area.
Exactly. And importantly, CNNs have very minimal inductive bias.
We need to define that. What is inductive bias?
Inductive bias is essentially the set of assumptions you program into an AI before it even starts learning.
Like rules of thumb.
Right. If I teach an AI to recognize cars, and I program an inductive bias that says cars must have 4 wheels, the AI will learn much faster. But it will also completely fail to recognize a 3-wheeled motorcycle because I artificially narrowed its worldview.
Okay, I get it. So by giving the CNN minimal inductive bias, the scientists are saying, we aren't going to tell you how fluid dynamics work. We aren't giving you any physics rules. Just look at the millions of data points and figure out the deep patterns yourself.
Precisely. They let the data speak entirely for itself, and the CNNs do learn incredibly deep, complex patterns, but that massive power comes with 3 severe drawbacks.
Okay, let's hear the bad news.
First, they are computationally ruinous. Ruinous. Running a CNN with millions of parameters at every single time step of a global climate model will bring even the most powerful supercomputers to a crawl. It defeats the purpose of trying to make the model faster.
What's the second drawback?
CNNs are fundamentally grid unaware.
What does that mean?
They treat the ocean data exactly like a flat 2-dimensional photograph. They don't inherently understand geometry. They don't know that the Earth is a sphere or that the grid cells in a climate model actually get physically smaller as you move from the equator toward the North Pole.
Oh, right, because the lines of longitude get closer together.
Yeah.
So the AI is looking at a distorted map and thinking it's reality, which means its physics calculations get completely skewed at the poles.
Exactly.
And what's the third drawback?
Coastlines.
Coastline.
The paper highlights that CNNs struggle massively with the boundary between land and water. When a CNN's 21 by 21 stencil swoops across the open ocean, it works beautifully. But when that stencil hits the jagged edge of North America,
Half of it is suddenly on land.
yes, suddenly half of its vision is filled with land data, which behaves completely differently than water.
It hits an edge case. Literally.
Literally. In machine learning, we call this an extrapolation error. The CNN encounters a specific permutation of jagged coastline that it rarely saw in its pristine training data.
And because it has no built-in physics rules,
Right, no inductive bias to fall back on, so it panics. It doesn't know how to interpolate the data, so it extrapolates wildly, outputting completely unphysical numbers like ocean temperatures of 1,000 degrees.
1,000 degrees.
Yes, which instantly crashes the simulation.
So a CNN is like a wildly brilliant chef who refuses to write down a recipe and who creates absolute masterpieces until you move the stove an inch to the left, at which point he gets confused and burns the entire kitchen down.
That is an incredibly apt way to describe out-of-distribution failure in deep learning.
I try.
So to avoid burning the computational kitchen down, the researchers looked at a more restrained option, Tier 2. Artificial neural networks, or ANNs. These are also known as multi-layer perceptrons.
How does an ANN differ from the brilliant but chaotic CNN?
They are much simpler, with a significantly lower software complexity. Instead of sweeping a massive 21 by 21 visual stencil across the globe, we explicitly feed the ANN highly specific localized variables.
Like zooming way in.
We only give it the data from a single point, say, the immediate shear of the water currents or the temperature gradient right at that exact location. And because the architecture is simpler, human scientists can easily inject some inductive bias back into it.
So we are putting the training wheels back on. We're telling the AI, here are some basic physics symmetries and scale invariances you absolutely must obey.
Exactly. It is a calculated compromise. You lose the deep, sweeping, non-local pattern recognition of the massive CNN, but you gain critical stability.
That makes sense.
The ANN is less likely to blow up when it hits a coastline, and it requires vastly less computing power. But the researchers didn't stop there. They pushed toward the most elegant, transparent option of all. Tier 3, equation discovery.
This one fascinated me. Are you saying the AI actually invents math?
Yes. Instead of the AI being a black box of millions of opaque, interconnected weights and neurons, the AI uses a technique called Bayesian sparse regression to search for a tangible, readable mathematical equation.
Okay, I'm going to need an ELI 5 explain. Like, I'm 5 for Bayesian sparse regression. What exactly is the machine doing?
Let's break it down. Bayesian refers to a type of statistics where you update your beliefs as you get new evidence. You start with a prior and initial assumption.
Right.
Sparse means we heavily penalize the AI for being complicated. We force it to find the simplest possible answer with the fewest number of terms.
Keep it simple, stupid.
Precisely. And regression is just the math of finding the line of best fit through the data.
So you essentially give the AI a massive library of mathematical building blocks, sine waves, derivatives, squared terms, and you say, combine these blocks to explain the ocean turbulence, but use the absolute bare minimum number of blocks you can, and keep updating your guess until it matches the data.
That is exactly it. And the result is stunning. The AI sifts through millions of combinations and hands the researchers a single, elegant mathematical equation.
Just a normal equation a human could read.
Exactly. The paper highlights one specific equation discovered this way, called ZB20.
So to go back to my analogy, if the CNN is the chaotic, brilliant chef who burns the kitchen down, equation discovery is like a meticulous, seasoned scientist who observes the ocean, distills everything they see, and hands you the exact formula for the perfect outcome on a neatly typed index card.
And the beauty of an index card is that it is infinitely easier to integrate into existing systems, which brings up a monumental, invisible engineering achievement of this paper.
What's that?
The researchers didn't just build these AI brains as abstract theoretical models, they did the grueling work of actually beating them into the MOM6 ocean model.
I saw MOM6 mentioned repeatedly in the paper. What is that?
MOM6 stands for the Modular Ocean Model version 6. It is one of the premier engines underneath the world's leading climate simulations, developed by NOAA's Geophysical Fluid Dynamics Laboratory, or GFDL.
Okay.
It is massive, incredibly complex, and it is written entirely in Fortran.
Fortran, that's a programming language from what, the 1950s?
Yes, the 1950s.
Why on earth are the world's most advanced climate models running on code invented before the moon landing?
Because Fortran is virtually unmatched when it comes to raw number crunching speed for massive arrays of physics equations running on traditional CPUs, it is the language of classical supercomputing.
But I feel a headache coming on.
Oh, it is a massive headache because modern artificial intelligence is almost entirely written in Python, designed to run on highly specialized GPU's graphics processing units. Python and Fortran do not natively speak to each other. Getting a modern AI to run inside a 1950s Fortran architecture is traditionally a nightmare.
It's like trying to install a Tesla autopilot system into a 1960s steam locomotive.
Exactly.
But how do they bridge that gap?
They built a custom, highly optimized Fortran module that serves as a translator. The heavy lifting, the actual training of the neural network using millions of data points happens offline, entirely in Python, utilizing massive GPU clusters.
Right.
Once the AI is trained, its final brain, its specific neural weights are exported and saved into a standardized format called a netcdf file.
So they essentially freeze-dry the AI's brain.
Yes. And then, when the massive global Fortran climate model boots up, the custom module reads that netcdf file, imports the frozen brain, and seamlessly executes the AI's predictions right alongside the classical physics equations.
That's wild.
It requires no specialized GPUs. It runs blazingly fast on standard CPUs.
That is a staggering logistical achievement, because it means you don't have to throw away decades of trusted Fortran code, and you don't have to force meteorologists to rewrite millions of lines of code into Python.
Exactly. And crucially, this setup ensures bitwise reproducibility.
Meaning what?
In software engineering, especially in chaotic systems like climate modeling, if you run the exact same simulation twice, you must get the exact same answer, down to the very last decimal point, every single bit of data.
Otherwise, you can't trust it.
Right. If the AI was constantly introducing tiny floating point math errors because of a sloppy Python to Fortran translation, the model would be impossible to debug. By hard-coding the neural network inference natively into Fortran, they achieved absolute repeatable stability.
Okay, so we've established the tools, we understand the limits of the pixelated grid, we see how the AI learns from microscopic simulations, and we understand the incredible engineering required to slide these AI brains from CNNs to index card equations directly into 1950s Fortran architecture.
Yes.
The obvious next question is, what actually happens when you flip the switch? When they turn the AI loose inside the living ocean model, did it work?
To test this, the researchers deployed these AI brains into the NOAA GFDL OM4 model. This model operates at a 1/4 degree horizontal resolution, so the grid boxes are roughly 25 kilometers wide at the equator.
Okay, we're in the gray zone.
Yes, and it also has 75 vertical layers slicing down from the surface into the abyssal depths of the ocean. They designed 2 very specific tests targeting 2 totally different physical environments.
Let's explore the first test, vertical mixing. This is the boundary layer where the ocean meets the sky.
Correct. It's the ocean surface boundary layer. This is where the sun beats down and heats the water, and where the wind whips across the surface, generating turbulent swirling that forces that heat downwards into the dark depths.
Right.
Now, what makes this test unique is that in the vertical dimension, we actually have a very clean scale separation.
Wait, how so? Because earlier we said scale separation was breaking down.
It breaks down horizontally. But vertically, the model's grid layers near the surface are extremely thin, maybe only 10 meters thick. The turbulent swirling that mixes the heat downwards operates on the scale of centimeters or a few meters.
Ah, I see.
Because the turbulence is so much smaller than the 10-meter grid layer, the old parameterization logic actually holds up pretty well here. There is no murky gray zone.
And historically, the model handled this vertical mixing using a classical physics scheme called the EPBL, right? The energetically consistent planetary boundary layer.
That's right. The EPBL scheme is highly respected because it enforces the conservation of energy. It never creates heat out of nowhere.
Good.
However, to calculate how fast the turbulence pushes the heat downwards, it relies on an ad hoc, fixed diffusivity profile. essentially a rigid assumption that dictates the speed of mixing regardless of the nuanced weather happening above.
So it's a blunt instrument. And the researchers swapped out that rigid, blunt assumption and inserted a dynamic AI-driven model.
Yes, they trained an AI on the perfect high-resolution simulation data, and they let the AI dynamically predict the rate of mixing based on the exact local wind and temperature conditions. But, and this is a critical detail, they did not throw out the EPBO completely. They kept the overarching physical energy constraints of the classical scheme.
So they put it in a box.
Exactly. The AI was allowed to predict the mixing speed, but it was operating inside a strict physics-based cage that prevented it from violating the laws of thermodynamics.
It's the best of both worlds.
Yeah.
You get the deep learning intuition of the AI, safely contained by the ironclad laws of classical physics. So what were the results?
The initial results were fantastic, specifically for the summer months. In the baseline model without AI, there was a persistent bias. The mixed layer depth, which is the warm, uniform top layer of the ocean, would routinely mix too deep into the ocean during the summer in the tropics and subtropics.
And the AI fixed that.
When they turned on the AI-enhanced diffusivity, it significantly reduced those biases. The AI correctly realized that the surface heating should suppress the deep mixing, and it adjusted the physics accordingly.
But I'm sensing a massive however coming. Did it fix the winter biases too?
It did not. In fact, the AI struggled significantly with the winter mixing dynamics. The improvements were highly signal.
Why? If it understands summer, why doesn't it understand winter?
Because the physical drivers are different. In summer, the dominant force is intense solar heating stabilizing the water. In winter, the dominant forces are harsh winds and rapid cooling, which causes the dense water to violently plunge downwards.
Totally different physics.
Exactly. The AI, trained on limited data, hadn't quite generalized the nuances of the winter convection process.
Fascinating. Okay, what about the second test? If vertical mixing was mostly successful because of that clean scale separation, how did the AI fare with lateral mixing, the horizontal churning?
This was vastly more difficult. Lateral mixing deals with the mesoscale eddies. And as we established, these eddies are 10 to 100 kilometers wide. The model grid is 25 kilometers wide. We are directly inside the gray zone.
Oh boy.
The model can almost see the eddies, but not fully. The Legos are exactly the size of the eyelashes.
A mathematical nightmare. How did traditional models handle this before AI?
Mostly, they just dumped horizontal friction into the model. They essentially added artificial viscosity, like turning the ocean into thick syrup, to smear out the messy noise at the grid scale and prevent the mathematical calculations from crashing.
But obviously turning the ocean into syrup destroys the realistic transfer of heat.
Yes, it ruins it. So the researchers tested two of our AI brains here to replace the syrup. The Tier 2 artificial neural network, the ANN, and the Tier 3 discovered equation, the ZB20 index card.
And what happened when they let the AI handle the gray zone?
The results were highly dramatic, but profoundly complicated. Let's look at the ANN first. When the ANN was turned on, it dramatically improved the ocean dynamics in the North Atlantic. Specifically, it fixed the path of the Gulf Stream.
Which is a huge deal.
It is an enormous deal. Getting the Gulf Stream right is a notorious problem in climate science. Traditional models often suffer from a separation bias, where the simulated Gulf Stream detaches from the North American coast at the wrong latitude, which violently alters the simulation of how much warm water is transported toward Europe.
And the ANN fixed it.
The ANN learned the correct subgrid physics and fixed the trajectory.
That sounds like a total triumph for deep learning. But I'm guessing there's another however.
A massive one. While the ANN was fixing the Gulf Stream in the Northern Hemisphere, it was simultaneously ravaging the Southern Ocean around Antarctica. It drastically worsened the warm temperature biases down there.
Wait, hold on. How is that physically possible? How can an AI perfectly fix the complex physics of the Atlantic Ocean while completely breaking the ocean around Antarctica? It's the same physics, right? Water is water.
It comes down to a deeply complex physical phenomenon called backscatter.
Backscatter.
When we think of turbulence, we usually think of energy dissipating, like a large wave crashing and turning into thousands of tiny, weak ripples. Energy moves from large scales to small scales.
Right.
But in the ocean, mesoscale eddies frequently do the exact opposite.
The opposite. The tiny ripples combine to make a massive wave.
Exactly. Small, subgrid turbulent eddies actually inject momentum and kinetic energy back up into the large-scale, visible ocean currents. This is backscatter. Now, the ANN, because it is highly expressive and highly complex, correctly learned to simulate this backscatter. That is why it fixed the Gulf Stream. It pumped the right amount of energy back into the current to keep it on track.
Okay, so why did it destroy the Southern Ocean?
Because the ANN is still fundamentally a black box. It learned how to inject energy, but it struggled to learn exactly when to stop.
Oh.
The Southern Ocean is a ferocious, uniquely energetic environment. The ANN essentially went into overdrive. It acted like a relentless anti-viscosity parameterization, constantly pumping unphysical amounts of kinetic energy back into the Southern Ocean, which resulted in drastically over-energized currents and severe warming biases.
It tried too hard. It found a hammer that worked in the Atlantic and then went down to Antarctica and smashed everything to pieces.
That's pretty much it.
What about the ZB20 equation? The simple mathematical index card discovered by the AI. How did that handle the test?
This is where the value of simplicity shines. The ZB20 equation is mathematically sparse. It has far fewer parameters than the neural network. When they plugged the equation in, it successfully improved the Gulf Stream in the North Atlantic, perhaps slightly less dramatically than the hyper-expressive ANM, but crucially, it did not degrade the Southern Ocean.
Because it wasn't complicated enough to overreact to the Antarctic currents.
Exactly. Its simplicity acted as a natural constraint. Because it was just a fundamental, readable mathematical relationship, it generalized far better across wildly different physical environments.
Okay, here's where it gets really interesting. As we're talking through this, I'm looking at my notes on the vertical mixing test we discussed a moment ago, and I need to push back on something because I think I've spotted a contradiction.
Oh, let's hear it.
You said the AI successfully improved the mixed layer depth in the tropics during the summer. It got the mixing right. But looking closely at the paper's results, it states that while the depth improved, the actual sea surface temperature, the SST, got worse in the tropics. How on earth can the AI perfectly fix the physical depth of the water mixing, but simultaneously mess up the surface temperature? Isn't the whole point of getting the mixing right to get the temperature right?
That is an incredibly astute observation, and you have just put your finger on the single most terrifying reality of global climate modeling. What you are observing is the sudden unmasking of compensating errors.
Compensating errors, meaning two wrongs accidentally making a right.
Exactly. Let me give you an analogy. Imagine you are captaining a large ship. Unbeknownst to you, your engine is broken. It's pushing the ship way too hard. But also unbeknownst to you, your heavy iron anchor is accidentally dragging along the ocean floor. The drag of the anchor perfectly cancels out the overdrive of the engine, and so the ship travels at the exact correct speed. You look at your speedometer, everything seems perfect.
Right.
Then an engineer comes along and says, hey, your anchor is dragging, let me pull that up for you. They fix the anchor. It is a perfect, scientifically sound fix, but the absolute second they pull up that anchor, the ship rockets forward at an uncontrollable speed and you crash. By fixing one error perfectly, you unmasked a second deeper error that was completely hidden.
Oh my God. So in the climate model, the old, flawed, rigid vertical mixing parameterization was accidentally acting like the dragging anchor. It was completely wrong, but its wrongness was accidentally compensating for some other massive bug hidden deep inside the model.
Precisely. We don't even necessarily know what the other bug is. It could be an error in how the clouds are reflecting sunlight or a bias in how the atmospheric wind stress is calculated. But the moment the researchers inserted the perfect AI-driven mixing physics, that accidental compensation was stripped away. The true underlying temperature bias of the model was suddenly exposed.
That is deeply frustrating. It means the entire legacy climate model is just this delicate, terrifying house of cards made of interacting mathematical approximations. If you meticulously fix the Queen of Hearts on the third floor, the entire structure might collapse because the Joker on the second floor was leaning on it.
It is the defining frustration of the field. And because of this terrifying reality, the researchers realized they needed a secondary strategy. If meticulously teaching the AI the perfect microscopic physics is constantly going to unmask other bugs and break the house of cards, they needed a totally different approach.
What's the new approach?
What if, instead of trying to teach the AI the perfect foundational physics, we just let the flawed model run and we use the AI simply to correct the final exam?
Oh, I love that pivot. It's an admission of defeat that leads to a totally new victory. And that brings us to the bias correction strategy, learning from mistakes. To understand this, we have to talk about data assimilation. Walk me through what that actually means in meteorology.
Data assimilation, often abbreviated as DA, is the backbone of modern daily weather forecasting. Let's say you have a model predicting the weather over North America. Every single day, that model runs its physics equations and spits out a forecast. But every single day, we also have real-world observations beaming down from satellites and data coming in from weather balloons and radar stations.
So you have the model's guess and you have the harsh reality.
Right. And data assimilation is the complex mathematical procedure of looking at the model's guess, looking at the satellite reality, and gently nudging the model back toward the truth. It calculates the exact difference between the two, and it generates an increment.
An increment, like a specific numerical band-aid.
Yes. The DA system might say, the model physics calculated the temperature in New York as 20 degrees Celsius. The satellite says it is actually 22 degrees. Here is an increment of plus 2 degrees. Add it to the model to fix the error.
And it does this constantly, every day, all over the world, just to keep the weather forecast from drifting into total fantasy.
Exactly. Now, here is where the researchers had a profound realization. Over years and decades of running data assimilation on these models, you accumulate an archive of millions and millions of these little increments. And if you look closely, those increments are not just random noise, they follow patterns.
Because the model is consistently stupid in the same way.
Exactly. They represent the systematic, ingrained biases of the climate model's underlying physics. If the model's cloud equations are slightly flawed, it might always predict that the Arctic is slightly too cold in November, which means the data assimilation system will constantly, systematically be generating +1 degree increments in the Arctic every November to fix it.
So instead of trying to fix the impossibly complex cloud equations that are causing the cold bias, you just train an AI to look at the archive of increments. You train the AI to memorize the pattern of the model's own stupidity.
Beautifully stated. The AI learns the state-dependent representation of the model's biases. It becomes an incredibly fast, highly accurate emulator for the exact errors the model is about to make.
How do they actually test this in practice?
They designed a massive multi-year experiment focusing on sea ice. They ran a global simulation using the GFDL SIS-2 model, a dedicated sea ice simulator. They took a convolutional neural network, a CNN, and trained it to predict the specific increments for sea ice concentration. Basically, they trained it to know exactly when and where the model was going to erroneously melt or freeze ice.
But wait a minute. Earlier you said CNNs were computationally ruinous. You said they dragged supercomputers to a crawl. How on earth did they run a CNN inside a global sea ice simulation without freezing the mainframe?
This is where we see some truly masterful software engineering. To understand how they made it efficient, we have to look closely at how modern supercomputers actually process global climate data. We have to talk about parallel processing architecture.
Let's get into the weeds. How does the architecture work?
When a supercomputer runs a global model, no single processor computes the whole Earth. It would be too slow. Instead, the computer carves the globe into hundreds of smaller, rectangular chunks. It assigns each chunk to a totally different processor. Processor A is crunching the physics for the North Atlantic. Processor B is handling Europe. Processor C is handling the Mediterranean.
So they are all working simultaneously to speed things up, but the wind blows from the Atlantic into Europe. The water flows from the Mediterranean into the Atlantic. How do the processors share the weather across the borders of their chunks?
They use something called a halo. Yes. To calculate what is happening at the absolute edge of its chunk, Processor A needs a little bit of overlapping data from Processor B next door. So, each processor stores a tiny halo of surrounding data, a buffer zone, usually a few grid cells wide, imported from the neighboring processors. In the GFDL model architecture, the default size of this memory halo is precisely 9 by 9 grid cells.
Wait, so they tailored the AI to match the halo?
Exactly. The researchers designed a highly specialized CNN with a visual stencil of exactly 9 by 9. When the AI is asked to predict the ice error at a specific point, it only looks at the 9 by 9 grid immediately surrounding that point. Because the AI's vision perfectly matches the pre-existing data stored in the processor's memory halo, the AI requires absolutely zero extra communication between the different supercomputer processors. It uses the data that is already sitting right there in the local memory cache.
That is just deeply, wildly nerdy and elegant. They literally sculpted the physical shape of the artificial intelligence's brain to perfectly fit the memory architecture of the 1990s parallel processing code.
It is a stunning optimization. And it paid off massively. Because of this exact alignment, running this CNN actively in line during a 5-year global sea ice simulation caused only a minuscule 0.3% computational slowdown on standard CPU clusters. It was virtually free compute.
That's incredible. So they built the perfect, lightweight AI Band-Aid. What happened when they let it run for 5 years? Did it fix the ice?
The results were genuinely remarkable. The CNN generalized beautifully to completely different environments in both the northern and southern hemispheres. When the free-running classical model erroneously melted ice in the Arctic summer, the AI dynamically recognized the error pattern and digitally added the ice back. When the classical model spuriously grew far too much ice around Antarctica in the winter, the AI recognized that bias and systematically removed it. The global sea ice biases were massively reduced across the board.
Okay, I'm waiting for the other shoe to drop. Let me guess.
Oh,
Compensating errors struck again.
you're catching on perfectly. Yes, compensating errors struck again. While the surface sea ice concentration looked pristine and realistic, the deep ocean beneath the ice, specifically the mixed layer depth, showed very mixed results. The ocean depth biases improved somewhat in the Labrador Sea and the Arctic, but they worsened significantly in the Weddell Sea down by Antarctica.
It really is like squeezing a balloon. You fix the bulge of ice on the top, and the pressure just pops out as a temperature error deep underwater.
Exactly. Changing the surface ice altered how much salt was rejected into the water when the ice froze, which fundamentally altered the density of the water, which changed how it sank. Fixing one variable always exposes hidden bugs in how the Earth's systems interact. But despite that, the overall data assimilation approach proved incredibly powerful.
But I have a fundamental question about the AI stability here. We established earlier that CNNs are prone to panic when they hit an edge case like the coastline problem.
Yeah.
If this AI is constantly running live, injecting new corrected numbers into the model every single day for 5 years, isn't it slowly pushing the model into a weird Frankenstein climate state that is never seen before?
Yes. You have just articulated the fundamental crisis of online generalization in machine learning. This is the hardest problem in the field right now. It is incredibly common for researchers to train an AI offline on historical data, and the AI looks like an absolute genius. It scores a 99% accuracy rate. But the absolute second you plug that AI into a running live climate simulation, what we call online deployment, it all falls apart.
Why? Walk me through the mechanism of how it fails.
The AI makes a tiny prediction error on day 1. Let's say it makes the ice 0.01% too thick. The climate model takes that slightly wrong ice, calculates the weather based on it, and steps forward to day 2. The model is now in a slightly weird state. The AI looks at this new weird state, gets a little confused because it wasn't in the training data, and makes a slightly bigger error. That bigger error feeds back into the model. Day 3 is even weirder. By day 20, the model has drifted into a totally bizarre, unphysical state that the AI has absolutely never seen before. The AI panics, outputs a catastrophic number, and the entire simulation crashes. We call it the spiral of death.
So how do you stop the spiral of death? How did they keep this 5-year simulation running without the AI panicking?
They solved it by forcing the AI to learn from its own mistakes. They used a technique called iterative residual error training. Here is how the mechanism works. First, you train the AI offline using the historical data assimilation increments, exactly as we discussed.
Okay, so you have a baseline smart AI.
Then, you plug it into the live model. You let the model run forward. Predictably, the AI starts making tiny mistakes, and the model starts to drift slightly off course into new, weird states.
The spiral begins.
But before it crashes, the traditional classical data assimilation system kicks back in. It looks at this drifting AI-corrected model and it compares it to the real-world satellite observations. It realizes the model is still wrong, so it generates a new increment to fix it.
Oh, I see. This new increment doesn't represent the original bias of the model. It represents the residual error. It represents the exact mistakes that the AI itself made when it was trying to fix things.
Exactly. The system captures the AI's own out-of-sample failure. So the researchers take all these newly generated AI-induced mistakes and they feed them back into the neural network for a second round of offline training. They essentially say to the AI, hey, when you encountered this weird climate state, you completely messed up. Here is the right answer. Memorize it.
That is so smart. By doing this iteratively round after round, the AI gets repeatedly exposed to its own out-of-sample errors. It explores the edges of the spiral of death, learns exactly how to correct itself, and fundamentally improves its own stability over time.
Yes, and the brilliance of this is that it bypasses a massive software hurdle. Some computer scientists argue that to train an AI properly online, you have to completely rewrite the millions of lines of core Fortran climate code into a modern differentiable language like Julia or JAX, so the AI's learning algorithms can penetrate the whole code base.
Which would take decades of man-hours.
Decades. But this iterative approach allows the AI to stabilize itself without ever needing to touch the core architecture of the classical physics engine.
To bring back my bowling analogy from earlier, the massive physics parameterizations we talked about at the very beginning, the EPBL mixing, the equations, guessing the turbulence, those are like scientists painstakingly trying to design the perfect aerodynamically flawless bowling ball and the perfect mechanical arm swing so that you get a strike every single time. It's beautiful, but if there's a speck of dust on the lane, it fails.
And the data assimilation approach.
This data assimilation approach is like saying, forget the perfect throw, just put up the bumper lanes. The underlying physics of the throw might still be slightly flawed, the ball might bounce back and forth a bit, but the AI bumpers guarantee that the simulation stays out of the gutter and eventually hits the pins.
That is a highly accurate and pragmatic way to look at the current state of hybrid modeling. We are building extremely intelligent bumpers, and that leads us directly into our final section today. Because both of these approaches, teaching the precise microscopic physics and putting up the AI bias bumpers, show immense promise in isolation. But the true final boss for climate modeling isn't just simulating the ocean in a box or simulating sea ice in a vacuum.
Right, it's tying the whole chaotic planet together.
Sure.
We're stepping into the final frontier, coupled systems and autoregressive emulators. So far, we've mostly been talking about the ocean acting alone. What actually happens when you hook all the different models together?
We enter the realm of fully coupled simulations. In reality, the Earth doesn't run its systems in isolation. A fully coupled climate model is a digital leviathan where the atmospheric model, the ocean model, the land surface model, and the sea ice model are all running simultaneously, and they are constantly talking to each other. At every single time step, they pass massive amounts of heat, momentum, and moisture back and forth across their boundaries.
Which sounds like an absolute recipe for chaos if even one tiny thing goes wrong.
It is a profoundly delicate knife-edge balance. And the paper details a fascinating, terrifying experiment that perfectly illustrates this danger. The researchers took that highly successful, incredibly stable ML-CS bias correction, CNN we just talked about.
The one with the 9x9 stencil that worked perfectly for 5 years.
Yes. They took that exact proven AI and they dropped it into a fully coupled climate model called SPEAR. In this model, the sea ice wasn't just existing in a vacuum. The atmosphere above it was live, active, and fully capable of reacting to whatever the ice did.
Okay, so the AI bumpers are on the ice, but the sky is now alive. Walk me through exactly what happened.
It resulted in a catastrophic runaway feedback loop. Here's the mechanism, step by step. The AI, doing exactly what it was trained to do, made a tiny, well-intentioned adjustment to the thickness of the sea ice.
It's step one.
Because the ice was now slightly different, it instantly altered the heat flux, the amount of warmth physically escaping from the ocean water into the air above.
Step two. The air gets warmer.
Because the atmosphere was fully coupled and active, this unexpected burst of heat triggered convective feedbacks in the air. The warm air rose differently. This caused clouds to form in totally different patterns than the model was used to. The different clouds caused the atmospheric pressure to shift, which caused the surface winds to completely alter their trajectory.
The ultimate butterfly effect. A tiny AI tweak to the ice completely rewired the wind patterns.
Literally. And here is the fatal blow. Those altered, unphysical winds then blew right back down onto the ocean. They churned up the water and preconditioned the ocean surface, which triggered a massive ice albedo feedback.
Let's define that. Albedo is reflectivity. White ice reflects the sun's heat back into space. Dark ocean water absorbs the sun's heat.
Exactly. The weird winds broke up a bit of the ice. The exposed dark ocean absorbed more heat. The ocean got warmer. The warmer ocean melted more ice. More dark water was exposed. It became an unstoppable chain reaction. Ultimately, the AI's tiny initial tweak caused the rapid, completely unphysical melting of almost all the summer sea ice in the Southern Ocean. The entire global simulation spiraled out of control and crashed.
Wow, so the AI bumpers completely failed, not because the AI was bad at its job, but because the atmosphere was allowed to fight back in a way the AI had never experienced. How did the researchers eventually stabilize it?
They realized they had to fundamentally change the AI's worldview. They couldn't train the AI on an isolated ocean model anymore. They had to generate a completely new training data set using what is called a nudged atmosphere configuration.
A nudged atmosphere. What does that entail?
They ran the massive fully coupled SPEAR model, but instead of letting the atmosphere run wild, they gently nudged the atmospheric variables like wind and temperature toward real-world historical data. It allowed the atmosphere to remain fully coupled and active, but constrained it to reality. They then trained the AI inside this nudged environment. This forced the AI to experience and learn the complex atmospheric feedbacks during its training phase. It learned that if it tweaked the ice, the wind would punch back, and it learned how to anticipate that punch.
And when they deployed this new atmosphere-aware AI into the fully free-running coupled model,
It was a massive success. The fully coupled SPEAR model stabilized immediately. It successfully ran a 7-year continuous integration without crashing, and it significantly reduced the sea ice biases while keeping the entire global system in harmony.
that is just incredible.
Yeah.
It highlights just how beautifully and terrifyingly connected everything on Earth is. You cannot fix the ocean without deeply understanding the sky. And looking at all this, the coarse graining, the fully coupled models, the Fortran translations, it makes me wonder about the end game. Where is this all heading? Are scientists just going to keep bolting these little AI bumpers onto legacy 1990s Fortran code forever?
Not necessarily. The paper points toward a horizon that is simultaneously thrilling and highly controversial. We are looking at the bleeding edge of the field. Autoregressive AI emulators. These represent a total paradigm shift. They are not just parameterizations of tiny subgrid physics. And they're not just bias correctors slapped onto classical equations. These are full, end-to-end artificial intelligence models of the entire Earth system.
Wait, hold on. Are you saying they are throwing out the Fortran, throwing out the Navier-Stokes equations, just building a giant neural network and telling it to predict the global weather?
That is precisely what is happening. You build a massive AI architecture, and you train it on decades and decades of output from traditional dynamical models, or on vast sets of historical climate reanalysis. You teach it the grand patterns of the Earth, and once that AI is trained, the advantages are paradigm-shattering. Primarily, the speed. These emulators are unbelievably fast. They can generate a highly accurate 10-year global climate forecast in minutes on a single GPU.
Minutes. Whereas a traditional supercomputer running Fortran physics might take.
Weeks or months.
That speed completely changes the nature of the science.
It democratizes it, and it allows for massive statistical power. It allows for enormous ensemble sizes. Traditionally, because compute is so expensive, a modeling center might run 1 or 2 forecasts for a hurricane track and just hope they captured the right variables. With an emulator, you can run 10,000 forecasts in an afternoon, each with microscopically different starting conditions. This gives scientists incredibly robust, high-confidence probabilities of extreme weather events.
You can see every possible future.
Yes. It also allows scientists to rapidly tune sensitivities. You can tweak a variable, say, doubling atmospheric CO2, and instantly see the global ripple effect decades down the line. Furthermore, you can use these hyperfast emulators to provide cheap boundary forcings. For example, you could use an AI to simulate the entire global atmosphere instantly, and use that AI-generated wind to drive a classical, hyper-high-resolution traditional ocean model, saving massive compute costs.
It sounds like a utopia. But there has to be a catch. We are talking about replacing centuries of fundamental fluid dynamics equations with a statistical black box.
And that is the massive existential risk the field is currently grappling with. Machine learning emulators inherently lack physical consistency. When a traditional Fortran model runs, its core architecture guarantees that the fundamental laws of nature are conserved. Mass is conserved. Energy is conserved. Water doesn't just magically vanish from the Earth, and heat doesn't spawn out of nowhere.
Because the classical equations physically forbid it.
Exactly, but an AI emulator has no such underlying physical loyalties. It is, at its core, a hyper-advanced pattern recognition engine. If it hasn't been constrained properly, an AI might accidentally create a massive burst of heat energy out of nowhere, completely violating the first law of thermodynamics, simply because it found a weird statistical shortcut in the training data that reduced its loss function.
It's essentially predicting the next pixel based on the last pixel.
Yeah,
It doesn't actually know it's looking at water or air. It's just playing a highly complex video game.
Precisely. And this brings us to the absolute frontier of this science today. The researchers highlight that the future is not pure AI replacing pure physics. The future is the deep integration of hard, immutable physical constraints directly into the architecture of the neural networks themselves. We are trying to build artificial brains that are statistically brilliant, capable of seeing complex patterns humans can't, but completely physically obedient to the laws of mass and energy conservation.
So as we wrap up this deep dive, I want to synthesize what this all means for the listener, for you and me. We have spent an hour talking about mesoscale eddies, 9x9 stencils, coarse graining, and fully coupled feedback loops. But practically speaking, this isn't just an abstract academic exercise happening in a basement supercomputer. The models we are talking about today, GFDL OM4, SPEAR, MOM6, these are the actual engines that generate the data for the IPCC reports. This entire conversation dictates the literal accuracy of the climate projections that governments around the world rely on right now. The AI predicting those subgrid eyelashes, the AI managing the heat transport in the Southern Ocean, is actively informing decisions about where to build billion-dollar seawalls, how to restructure national agriculture for the next 50 years, and how to prepare populations for unprecedented drought. Getting the physics of a 10-kilometer whirlpool right using a neural network could quite literally be the difference between a resilient, prepared city and a flooded one.
That is the stakes of the game. The transition outlined by Dr. Zana and her team in this paper, moving from pure classical physics to hybrid AI parameterizations to inline bias correction and eventually to physically constrained full emulation, is not just an upgrade in software. It is arguably the most significant revolution in Earth system modeling since the invention of the numerical computer itself in the mid-20th century. We are redefining how we perceive and predict our own world.
It has been a truly incredible journey today. Just to briefly recap the ground we've covered. We started by confronting the pixelated limits of our current supercomputers, realizing that the old Lego blocks are too big to capture the crucial turbulence of our oceans. We explored the brilliant transition from traditional rigid physics parameterizations to AI-driven coarse graining, where the machine learns the missing physics from pristine, microscopic large eddy simulations. We talked about the monumental invisible engineering feat of sliding modern Python neural networks directly into 1950s Fortran architecture to achieve bitwise reproducibility. We witnessed the AI successfully fix the Gulf Stream, only to break the Southern Ocean due to the complexities of backscatter and compensating errors. And we navigated the wild reality of data assimilation, where an AI acts as a bumper lane, constantly watching a model make mistakes and learning to correct its biases on the fly, narrowly dodging the catastrophic butterfly effects of the fully coupled Earth system.
It is a massive amount of highly complex science to take in, but I truly encourage you, the next time you glance at a daily weather forecast on your phone, or the next time you read a headline about a major international climate report, to look a little differently at those predictions. Realize that beneath the smooth surface of that data, there is a hidden, incredibly complex battle and a beautiful collaboration happening right now between the raw equations of classical physics and the cutting edge of artificial intelligence.
It is profound. And it leaves me with one final thought, tying all the way back to the very beginning of our conversation. We started by talking about the X-ray, the deep human desire for a clean, visible, perfectly understandable diagnosis of our planet's future. If we eventually succeed, if we pour enough data into the system and build a massive, perfectly constrained, autoregressive AI emulator that can flawlessly predict the Earth's climate down to the millimeter, forecasting every hurricane, every eddy, and every drought with absolute precision over the next century. But the inner workings of that system are just billions of opaque, tangled neural network weights that no human mind can actually read or intuitively decipher. Have we actually understood our planet, or have we just successfully cloned a mystery? Until next time, keep diving deep.